Hi, before the video starts, this is the editor speaking, and I'll be giving just a brief disclaimer that the start of the video was lost due to technical difficulties, and instead I'll be giving just a brief explanation of the context surrounding the lesson. So today's lesson was presented by our own teacher, Mr. Schattman, who is our grade 12 and grade 11 computer science teacher at Sir John A. Macdonald Secondary School. And today he was teaching us about creating 3D graphics using processing, a fairly easy to use that's programming language that's taught in the grade 12 course. And Schattman was giving a brief explanation of just instead with 3D graphics, sometimes it's easier instead of rotating an object to change the camera, and he's going over the code for simple 3D graphic project that shows us camera control as well as drawing 3D.
Where I want to put it, what it's going to be looking at, and which way is up. Can anyone guess what 0, 1, 0 means? What do you think we're telling processing with those three numbers? Someone type a guess in the chat. It really is a 1. So Robert is on the right idea that these are specifying which way is up. These are all good guesses. What this is really saying is that this refers to the x-axis, the y-axis, and the z-axis. And we're telling processing, I want the y-axis to be up, and this to be left and right, and this to be in your face. That's sort of the idea. Okay, now that I've placed my camera, now I'm ready to draw my scene. And in this case, I'm simply going to draw some x and y, z axes, and then I'm going to draw this box in the middle of my field. We'll come to these angles in a minute. Later, we're going to be changing angles, and later we're going to be moving the camera with time. But for now, we're just going to leave the camera there, so ignore this for a second. Let's see what draw my box does. Actually, I'll just show the program. Here it is. Okay, I have this box sitting in the middle of space. And these yellow, white, and green lines, these are axes. So this white line is the x-axis. This yellow line is the y-axis, and the green line is the z-axis. Now, it looks like it's kind of going off into the corner, but imagine we're sort of sitting in this room, and this place here is the upper left corner of the room, so you're looking up at it. So it actually looks like this line is kind of going off to your diagonal left, but really it's kind of pointing out into space. Let me draw it without the box, just the axes. So I'm going to turn that line off. All right, these are just my axes. Now, notice what happens if I change where my camera is. I'm going to move my camera to the left to be 100. So I'm just barely to the left of my screen. And now the upper left corner is kind of looking like that. Let's move this back to the middle, but now I'm going to move my eyeball up towards the ceiling, so more like 100, so not too far from the top edge of the screen. And now let's move this like very close to the left edge, like 10. And there we go. And on and on. Okay, let's put this back. So we had 400. Now let's put the box back in. But now let's show how we actually draw this box. So I have this procedure called draw my box, where I fill it with some kind of color. In this case, it's kind of shade of green. And then there's a command in processing called box, which tells you that it's going to be this wide, this long, and this deep. What if I made this a larger number? Let's make this like 500 instead of 50. So it's a much deeper box now. What if I make it wider, but not so deep? And there we go. Now, by default, processing, when you say box, it draws your box as if it were at the origin. It always draws around the center 0, 0, 0. So 0, 0, 0 is right in the middle of the box. But what if I want my box to be somewhere else on the screen? In that case, what I do is called translation, where I say, with this command, I'm saying, hey, processing, I don't want the origin to be at 0, 0, 0. I want the origin to be at this location. So think of this as 0, 0, 0, and now draw a box around this location. We'll rotate in a second, just kind of ignore this, but for now, we're just sort of translating. Let's see what happens. So now the box is there. Let's make it a little bit smaller. Okay, there's my box. Now, what I'd like to do is move my camera from, say, left to right. Let's put the box more in the middle of the screen. And now let's train our camera to move a little bit. So let's move from left to right. So that means I want this xi variable not to be constant at this 400, but increase by, say, 10 pixels per frame. Now let's see what happens. And goodbye box. And axes. How about instead of this, let's make this 0. Let's move up. So that means I want to go up by, say, -5. And now we're flying through the ceiling, off in outer space. And there we go. And goodbye box and goodbye room. Okay, let me stop right here and pause for any questions. If you are feeling good and you're understanding everything so far, give me like a thumbs up or something. If you have a question or you're confused about something and you want me to clarify, type a question. I give you 10 seconds to give me an answer. Okay, so I got a couple of good questions here. So Andrew's asking, are these functions built in? Yes, so this function camera, this is built into processing. And this function, where is it? Box, that's built in. Translate is built in, so I didn't have to code any of these procedures myself. Someone else was asking, why is it harder to spin the object? Well, we're actually going to get to that. So I'm going to show you another application where we actually make the object spin, and we'll see how easy it is compared to actually doing it the traditional way. And someone else was asking, can you change the frames per second? Yes, you can. So inside setup, by default, it's going at 30 frames per second. So in processing, you can say frame rate. And if I say 40, that'll say 40 frames per second. I think by default, it's 60. If you put it anything less than that, then it'll go slower. So watch this. So that's a much slower animation. But for now, we'll just leave it at 60. All right, these are all good questions. Okay, let's move on. What I'd like to do now is try rotating these objects. So let's come to where my box is. Sean is asking, are we supposed to be programming this on your computers? No, you're supposed to be watching me and being totally enthralled by my amazing presentation skills. What I will do is give you the code later for you to play with at home. But for now, you can just watch. Cool. Okay, so in addition to translating, I can also rotate an object before I draw it. So what we're saying in processing, hey, draw a box with this size centered around this point. But before you do that, let's rotate it a little bit. So I'm going to, excuse me just a second, someone's ringing the doorbell. I'll let them in. Okay. All right, so I'm going to rotate by around the y-axis. So let's kind of see what that looks like for a second. Let me just look at the axes themselves. Let's just draw the axes. And let's not go anywhere. Let's turn this back to 0. Okay, here's my axes. There are 3 ways to rotate an object. You can choose your x-axis as the axis around which you're spinning. So imagine something moving around the x-axis. Or you can choose your y-axis to be the axis of rotation, move around in a circle this way. Or you can revolve around the z-axis and move this way. And we can specify one of those things inside processing. So what we're going to do is we're going to rotate around. Let's pick the z-axis first by some angle phi. And phi is going to be set to 0 at the beginning, but every time we repeat, I'm going to make phi increase by a small amount. All right, here we go. And let's draw our box. Okay, this is not very impressive because it looks like it's a rectangle rather than a box. So what I need is a better perspective. Let's not look at the thing from square on. Let's make my yi a little bit above the box. So let's come up here. So I'm looking down at the box from below. Now we can start to see its 3 dimensions. Or let's look at it from below instead of from above. Let's go below the halfway point. Let's select the view from 700 down here. Okay, so that is spinning around the z-axis. Yeah. Let's try spinning around one of the other axes. Let's rotate around the x-axis this time. And you can see if this is the x-axis, imagine that this is kind of skewering the box from top to bottom like a popsicle. Now it's rotating around the popsicle stick. Okay. Do you think it's possible to rotate around 2 axes at the same time? Like if I say inside here, could I rotate around the x and the z by 2 different angles? Would that be amazing? What if I could make some angle here, theta, and we're going to make theta increase by some small amount. Let's take a poll. Give me a thumbs up if you think this is possible, and thumbs down if you think it's going to crash. Let's hear it. All right, everyone has faith in the power of technology. Thumbs up squared, says Ohm. I like it. All right, let's put our money where our mouth is and see if this works. Here we go. And we have a tumbling block, as if it were falling. Now, let's crank this up a little bit. That's too slow. That's like 0.05 in the phi. Here we go. Pretty cool, eh? Now, what you might notice is that the axes themselves are not rotating. We're only rotating the box itself. Okay, let's stop this for a second. A little bit more technical detail about how this works. So whenever you want to draw an object around the origin, but before you want to move it to another location, then rotate it, you put all these are called transformations. And you put all your transformations between 2 commands. This command here, push matrix, that means basically start the transformations. This command here, pop matrix, means basically end the transformations. The reason you need to get rid of them, the reason you need this, if I took this away, then that would mean every single frame, it would push an additional 400, 400 up down and to the right. And in every single frame, these phis and thetas would build upon themselves in successive frames. Basically, I want these numbers to start over in every single frame. That's why I enclose them here. Okay, let's actually make a tetrahedron now. So we've been doing a box. Let's make a tetrahedron. So in the box, there's a built-in procedure called box. But for drawing a tetrahedron, there is no built-in procedure called tetrahedron. So instead, I have to make it myself. And the way you can make your own shape is you use a command called begin shape and end shape. And in here, I simply draw a bunch of vertices which I connect together. This means I'm going to take this vertex, connect it to that one, connect it to that one, connect it to that one, in sort of a continuous shape. And this tells me I'm done. And you notice that these points are all centered around the origin 0, 0, 0. So let's come back to my main program here. We have our camera. Let's be centered more normally here. Let's get a little bit closer to the action. And let's not draw a box. Instead, we're going to draw a tetrahedron. Like so. And let's not rotate just yet. We'll do that later. You see anything? It's right here. It's way far away. So, okay, that's way too far away. So let's get a little bit closer in. Oh, I said 7,000. No wonder. Duh. I was wondering what on earth was going on. Okay, let's take off a 0. See if that helps. Okay, there it is. Somebody answer me. Why do you think we only see the lower left corner of it? Why do you think that's happening? Okay, because of the camera position. And Sean, you have the right idea because we haven't translated it yet. That's correct. We haven't done a push matrix. Correct. So let's come back to my tetrahedron here, and let's turn on some translations. So let's not rotate yet, but let's move it to this center place, which I'm going to define. Okay, I'm going to move it to basically the center of my screen, and now run it. All right, there it is. Oh, wait, what is it complaining about? Too many calls to push. Oh, I forgot to turn on puff matrix. That's why. Okay, it looks like a kite. This is not very interesting. Why is it looking this way? Because I'm looking directly from above. So I need to move my camera a little bit to look at it from another point of view. So let's move my camera a little bit farther to the right and a little bit above. And let's back up a bit to 1,000. Ah, there's my nice tetrahedron. It wouldn't it be cool if we can make our tetrahedron rotate just like before. So let's put some rotation in there. And let's go ahead and rotate by phi now. Yay, spinning tetrahedron. Is that amazing? All right, wouldn't it be cool if we can, Timothy's saying, can we fill it with color? Yeah, I think we could probably do that. Let's see what happens. Let's see. So we have a stroke and a stroke weight. So let's end it into a stroke. Let's do a fill. What color should we do? How about some cyan? So no red. Let's have maximum green and maximum blue. And we're going to, let's see what that looks like now. That did not work. Okay, maybe not. So on another day, maybe I'll learn how to do this. I actually don't know, so you called me out. Maybe one of you geniuses can figure it out. Anika's asking, does processing not support hex codes? It does, yes. So you can specify this in hex as well. So I could say like hashtag FF00B4 if I wish. And I have that, yeah? So we can do this. How about we rotate the thing and move the camera at the same time? Now, Anika just typed an OO with 3 O's. When I show you this, you're going to be typing OOs with multiple O's, like way more than 3. You're going to be OOing so hard, you're going to run out of O's. So let's make the camera move now. Right now, the camera is stuck at this point of view. And right now, I'm not increasing anything. What if we could move the camera, let's say like 5 pixels to the right every time? And let's start farther to the left at the beginning. So we're going to start at 100 and move to the right. Here we go. And goodbye, tetrahedron. Very cool, eh? Ah, nice. Oh, very nice O's. Thank you, Varun. You just set a record for the number of O's in an OO. At least in one chat. And one giant O from NASA, which I'll take that's good news. Because we all know big O notation, right? Oh no, O to the power of 100. That's more than the number of particles in the universe. This is okay. Okay, so that's some basics. Let's now put this to some more interesting use. I'm going to show you a different program now. So we'll save that, and I will put that code on the Classroom site for you guys to play with later. Let's take a look at another program called the Jenga Stack. If you guys have ever played with Jenga blocks, you'll recognize this picture. So this is a stack of blocks that I built at the Children's Museum years ago with my daughters because we were bored one day. The exhibits were dull, and so we took a bunch of Jenga blocks and kind of built these into a stack like this, where every piece is just a little bit rotated from the one before, so you get this nice spiral staircase look. Let's write a computer program in processing that will make this picture. So here we go. So in this program, I can specify how wide I want my blocks to be, how thick they are, and how long I want them to be. So Jenga stacks are really long and thin, so this is a big number and this is a relatively small number, and they're a little bit wide across. Don't worry about this stuff for now. So inside setup, what I do is I make a size. I only want my screen to be 300 pixels wide because these blocks are not very wide, but I want it to be very tall so I can make a long stack. And once again, I say P3D to go into 3D mode. Well, once again, I'm going to be drawing in the dark because I like darkness. Let's have a pretty thick line there. Don't worry about this stuff for now. Mostly the important part to worry about is draw. So once again, black background. And before we start drawing a block, what I want to do is make the first block appear at the bottom of my screen in the middle. So let me show you what happens if I don't translate anywhere. So you see up in the left corner, I have these blocks that are kind of being created, but they're way off in the upper left because it thinks that 0, 0, 0 is way up here, so it's drawing around the origin every time. But what I want is the first block to appear at the bottom, then the next block to appear slightly above it, then the next block slightly above it, and so on. So that's where translate comes in. So what I want to do is before I begin, I want to move my origin to the bottom center. So this is close to the bottom because this 810 is close to this 950. And this is the middle left and right, so that's half of 300. But I don't want to move in and out. So I don't want my face in the middle of the blocks, and I don't want to be so far away. So I'm going to leave that at 0. Now what we're going to be doing is in a for loop, we're going to go up to the number of blocks, and every time we draw a block, we're going to draw it in space. Then I'm going to increase this angle by which the thing is drawn. So when I draw a single block, I'm going to draw a box, just like before, which has a width, a thickness, and a length. Why do I put the thickness in the middle? Because this is the y coordinate. I want y to mean up and down. And this is the z coordinate, so the long block is going to be pointing into our faces. Ouch, it hurts. It pokes us in the nose. Now, once I've picked my origin at the bottom, my first block is going to be almost at the bottom, but then the next time I draw a block, I want to move a little bit up. How much up do I want to move? By the thickness of one block. Therefore, I make this negative block thickness. But I do not want to move left and right, and I don't want to move into the screen. So I'm just going to leave it there, and then I'm going to rotate by about the y-axis. Remember, that's the axis that points up and down by some small amount. Let's see it go. You ready? Drum roll, please. Okay, let's try it with some other options. Glad you enjoyed. Isn't that cool? I love this. I love seeing stuff in the physical world and writing a computer program that does it. That's my greatest joy on earth. Okay, so let's change some things. So I can mess around with these numbers here. What if I could make my blocks thinner, like 4, and even longer, like say 350? And what if I could go, say, 4 full circles? And let's speed up the animation a bit. Number of frames per second is 10. So when I do my, where's the frame rate? Yeah, so I make my frame rate equal to whatever this value is, which is this number here. Now let's go. Okay, so my screen is not wide enough. So let's make my let's make this a little bit larger here. So let's make this 600, which means I also need to change what? I also need to change this, right? And off we go. Nice, eh? And we can make this as tall as we want. Likewise, what happens if I don't fill? So I have this little option here where I can let the user pick fill or not. So I've set to true. What if I set this to false? What does that do? If fill is set to false, then I'm not going to fill it. I'm just going to use a stroke, meaning it's going to be a hollow box. Otherwise, I'm going to fill it with this nice brown wooden color, which I found online, and have a black stroke. Let's do it with one of these guys. Let's go back to the original numbers, though. Let's have like 8. You get something like an ice sculpture. So you can see through it. It's kind of neat. Yeah, it's like DNA-like, right? Okay, now let me change one thing for you before I show you a different program here. Now notice I was translating by 1 block thickness worth. What if I made this more? Let's go back to normal filling. I'm going to say not minus block thickness, but minus 3 times block thickness. I'd like you to imagine in your head what you're going to see before I run the program. I'll give you 10 seconds to think. I lied, 8 seconds. Here we go. So now we are defying the laws of physics. That's the wonderful thing about computer programming, is that your laws don't have to make physical sense. You can do anything that you want. Anything your mind can imagine, you can draw it. But most of the time we want our pictures to kind of look realistic, so that's why we have this little thing here. Minus block thickness. All right. I'm going to show you a better version of this. Save. Let's actually make the thing rotate in space. Let's do a rotation version. Okay, first a little hard math. I need to show you something called spherical coordinates. Because what we want to do is make our camera move in a circle. In the first 2 examples that I showed you with the box and the tetrahedron, the camera was just moving in a straight line. But what I'd like to do in this example is move the camera in a circle around the stack of blocks so that it looks like we're in orbit around the stack. Now to do that orbiting, we need to learn a little bit of mathematics called spherical coordinates. This picture on the right is something that you would have learned in my grade 11 class or even my grade 12 class, where if you have this angle here and you have this radius r, the width of your triangle is the radius times the cosine of that angle. And the height of the triangle is the radius times the sine of the angle. You guys learned that in grade 11. I beat it into you. In 3 dimensions, it's even cooler. Imagine that we have our x-axis here, our y-axis there, and our z-axis pointing upwards. And we have this point sitting out in the middle of 3D space. And suppose this point is, what is the letter? Rho, I think that Greek letter is called. The Greek letter rho, units away from the origin. And what I want to know are, what is its x-coordinate, what is its y-coordinate, and what is its z-coordinate? Given what? Well, I'm given 2 angles, actually. In the 2-dimensional case, I only have one angle to worry about. I'm orbiting around the z-axis, which is actually not visible. Like the z-axis is poking you in the nose. You can't see it, but that's the angle, that's the axis about which I'm rotating. And that's the same happening with theta down here. Theta is rotating around the z-axis, which is visible now because we've moved it. But now we have this other angle we can play with called phi, where phi is the radial distance from the z-axis. So I can kind of pull this point away by this angle. Now, given these two angles, can we compute x, y, and z? Here's some equations. So here's another picture of the same thing. I have this point out in space called P. Oh man, they messed up my angle. So they're calling this phi, this theta, but whatever. I'd like you to stare at these three equations for a second. I want you to be confused, and then I'll explain it. Okay, you've had sufficient time to be confused. Let's explain. So this angle theta here, let's first figure out the length of this diagonal line. Like, how far is this point from the z-axis? Well, I have the opposite here. So this length here is this radius times the sine of the angle. That's this length here, which I can copy down to the onto the floor right here. So this length here is r times sine theta. Make sense? Of course it does. Now, how do I get this length? Well, now that I know this length, I can calculate the cosine of this angle. That'll get me the projection on the x-axis. So if I take this length right down here on the basement, which is r sine theta, and now multiply that by the cosine of that angle, that will get me the x-coordinate. So notice x is r sine theta times cosine phi. Whew, that was a lot of talking. Thumbs up if that made sense to you. Thumbs down if I lost you totally, which is okay. Okay, very good. So by similar reasoning, I won't take you through the whole thing. The y-coordinate for similar reasoning is r sine theta times the sine of phi. Now, z itself is the distance from the origin up to this point where we're cutting off. How do we get this distance? Well, you take, that's adjacent to the angle theta, so it's simply r cosine theta. So z is actually the easiest one to compute. Okay, memorize these formulas. I'll give you 5 seconds. 1, 2, 3, 4, 5. Okay, time's up. Let's go back to the program. Not this one. Jenga Stack. Right. All right, let me show you these things in action. So in my draw procedure, those are those formulas that I just showed you. Except y is the axis that's pointing upwards, not z. So this is the one that gets the cosine phi, and the other two are the hard ones. So z is kind of taking the place of the x-axis. So there's the x-axis thing, there's the y-axis thing. And the radius is how far I am from the stack. So this is like my r. And I'm going to specify that at the top to be some big number. So I'm going to be 1,000 pixels away. Okay, so what I want my x, y, and z to do, I want my x-axis to be this far away from the center of the screen. So if these were all zeros, this would mean I would be rotating around the origin in the upper left corner of my screen. But instead, I want this to be around the center of the screen, pretending that's my origin. This doesn't really need to be here, but that just reminds me. Now I'm going to set up my camera at this location, pointing at the center of the screen where the y-axis points up. That's where my camera is. Now, I'm not going to draw my blocks one at a time like I did in the first program. Instead, I'm going to draw these all at once in a single while loop rather than one at a time. So I do my translation, draw the blocks, and then pop matrix as soon as this is done so that the blocks don't compound their transformations on top of each other. That's one iteration of draw. Then when draw calls itself again, what I'm going to do is make one of these things change. Actually, what I want to do is make these angles change so that I move around the circle. Let me just run it in this mode first. So this is the normal stack. We're not moving yet. Now, I want to move one of these angles by a small amount every time draw repeats. Quiz time for you. Which angle should I choose? One of these, something, is going to be plus equals some small amount. Think in your mind? Well, I'm too lazy to figure out, so I'm just going to try one of them. Let's try theta first. And lo and behold, we have a spinning spiral. Isn't that beautiful? Now, is the spiral actually spinning? No. What is spinning? It's we, the viewer, who are moving around the spiral as if our heads were in orbit around the stack. That's what we would be seeing if we looked at it in that way. Yeah? All right. Now, instead of theta, what if I make phi the one that's changing? Can you imagine what you're going to see? Here we go. Very nifty, eh? And of course, we could do both if we felt like it. All right, pretty beautiful stuff. Okay, for our last example, folks, I'm going to show you what's called the Sierpinski Pyramid. First of all, a little poll. Give me a thumbs up if you have heard of the Sierpinski Triangle before. Thumbs down if you haven't yet, which is okay. Thumbs up if you have. Okay, a couple yes, a couple no. Okay, not a problem. Okay, so let me just show you quickly what the Sierpinski Triangle is, and that'll show you the Sierpinski Pyramid. Let's go to images here. Okay, so here's the idea. It's basically a fractal object where you cut a triangle out of the middle, and then from what's left, you cut another triangle out of those centers, and then from what's left, you cut a little triangle out of those centers, and so on, as many levels as you want to do. And it's a fractal object. There is a three-dimensional version of this called the Zabinsky Pyramid. Which looks kind of like this. I think that's the best picture of it. Let's open that up. We're going to write a processing program that draws this. And not only draws it, but rotates it. And not only rotates it, but we're going to fly through it as if we were a drone. We're going to fly right through those holes and look at the thing from the inside. That's going to be amazing. You're going to be so out of O's, you're going to be in O debt for the rest of your life. Here we go. All right, so I'm going to turn off rotation for now. Let me just make sure we're set up in the right way. Actually, I'm going to freeze that. Let me draw you at a low level first. Okay, this is the Sierpinski Pyramid drawn from one point of view. And let's actually start to rotate it a little bit. So here I'm using the exact same techniques that I did to move around the Jenga stack of blocks, but now we're using a Sierpinski Pyramid. We're going to fly through it later. I'll show you that piece later. Let's do the rotation first. Now, this is level 3. What if we look at level 4? You notice that there's more detail now. And then we're going to fly into the interior. Do a little spin and back out. Yeah? Okay, let's do a higher level. Let's do level 5. So more detail. And this part you know. Let's go to even one higher level. 6. So every time we go up one level, we increase the number of triangles by a factor of 4. So that's, you'll notice it's lagging a little bit. That's because it's taking my poor CPU a long time to compute this object. There it is in all its beauty. And now we'll do the fly through. Here we go. Fasten your seatbelts, folks. Here we go. When you run it yourselves on your home computers, it'll look way smoother. Right now it's lagging because of the broadcast, but here's the idea. So Hill, what is an NFT? What is English for the old guy here? Oh, okay, whatever that means. Thanks. Okay, let's take a look at the code a little bit in detail. So I won't take you through all this because this was actually several weeks worth of coding, so I don't want to bore you with all the details, but the point I want you to see is, which part do I want you to see? Okay, this part is exactly the same as what I showed you in the stack of the Jenga blocks, but with one key difference. Can anyone spot the difference? What's different in these 3 lines of code that we didn't see in the Jenga stack? Aha, Anika has found it. It is this piece right here. This didn't used to be there. So what we're doing is we're saying, okay, your position in X, Y, Z space is going to be dictated by the angles that you're at. And what we're doing is we're making theta and phi increase by these amounts. But we're also going to fly into it. So we're going to make the z-axis poke us right in the face. Our heads are going right towards the computer screen until we break it. That's what this is doing. This is exactly the same. This hasn't changed. We've added a little lighting here, which I'll go over in a bit. And now what do? Once we've set our camera, what we do is we pick 5, we're going to pick 4 points. That's going to form the extreme 4 points of my giant pyramid. And within these, I'm going to build my structure using a technique called recursion. So I take these 4 points, A, B, C, D, and I pass them as parameters to a procedure called draw Sierpinski Pyramid, where I tell it what level I want to draw out. Remember when this is like 3, it wasn't a very detailed triangle. That was more detailed, and so on. Like this. Now let's see how this works. So here's my procedure for drawing the Sierpinski Pyramid. So I take a point A, a point B, a point C, and a point D. These are all 3D points. If the level is 1, all I do is I draw a simple pyramid with 5 points. 1, 2, 3, 4. Sorry, 4 points. A single square-based pyramid. In fact, let me show that to you. What happens if I set the level to 1? That's the most boring Sierpinski pyramid in history. It's just a single pyramid with no structure in the middle. So these 4 boxes, these are my points A, B, C, and D. That's what these are the 4 corners. Anika's asking, do the boxes have to be there? No, they don't. We can turn those off, actually. I'll show you how we can turn those off in a minute. Now, what do? In order to build the structure in the middle, you calculate 9 midpoints on the pyramid. You calculate the midpoints of the 4 sides of the square base. Sorry, 3, not 9. This is wrong. This looks like 6. My fault. I should say for the triangular base. And then 3 for the lines connecting the peak to those bases. Now that I have these midpoints, I'm going to draw a level -1 pyramid in 4 places. 1 in the lower left, one in the lower right, one in the back, and one on the top. So I get 4 more recursive Sierpinski pyramids stacking into the 4 other levels of into the 4 corners of my pyramid using these midpoints that I just computed up here. So these MABs and MADs, these are taking the place of A, B, C, and D, and so on. If you take my grade 12 computer science course, this will make more sense to you when we study recursion. But for now, this is like a 5-minute version of recursion. All right. Now, what happens in level 1? In level 1, I just draw a simple pyramid, no recursion. How do you draw a pyramid? Well, here's my function for drawing a pyramid. I take 4 points, A, B, C, D, and I just draw a bunch of lines. So first I draw the base. I draw 3 lines for the bottom of the triangle. Then I draw lines connecting the base to the peak. There they are. So a total of 6 lines. 1, 2, 3, 4, 5, 6. Now someone was asking about boxes. Next, I draw boxes around these points. How do I do that? I had to code that myself. So when I look at these are point 3D objects. So in my grade 12 class, you're going to learn how to make classes. This is called object-oriented programming. So in my point 3D, every point has an X, Y, and Z coordinate, but we can also draw a box centered around that location. Notice this. You've seen that before. You've seen that before. You've seen this before. And we're going to translate to this location, wherever the box happens to be. That's these guys right here. Now, what if we turn this off? Let's comment these lines of code out and draw our thing now. And when you get closer, you'll notice there's no boxes. So notice the boxes are gone. In fact, if I draw the level 1 version, it's just a bunch of boring lines. Yeah. Okay, folks, this took me way longer than I thought. I have one more thing that I was interested to show you. It involves some pretty heavy math, and I realize not everyone would want to listen to that because you've been listening to me for an hour already. So before I jump into that new stuff, I will give you a chance to quietly slip away without shame, and I will not judge you. If you want to ask questions for a minute or two to give cover to the people sneaking away, you can do that now. And then after the questions are done, I'll show you the advanced math for moving the camera in a very particular way. It involves, that point where you turn around, like you're going through the pyramid and you suddenly turn around. How you do that smoothly requires some pretty intricate math, and I was going to show that if you're interested. But first, questions. Andrew's asking, can we compile the program separately without rerunning the thing? Yes, there is. So you can do what's called creating an, let me quickly show you. So if you were to go to File, where is it? Export Application. This allows you to create basically a Windows executable file which doesn't have to rerun every single time. And basically it'll create an executable that you can now send to people, and they can double click and run it without having processing installed on their computers. Someone else had a question here. Let me check the chat. Oh, Alm was asking, is there a way to add sound and processing? Yes, there is. Let me show you some other features of it. So if you go to the Tools menu and you go to Add Tool, you can import stuff that isn't normally built in. So if you go to Libraries, there's something for sound, I think. Which one is it? I think it's Minim. Yeah, so in fact, one of your classmates who's listening right now, Yina Gao, made use of this. So if you'd like to learn how to do this, you can pester her, and I'm sure she will help you out with that. Yes, that's right, Nassif. All right. Any more questions before I jump into the cool stuff? As if there's one cool already. All right, if you have had enough, this is your time to slip away. And if you want to stick around, please do. I'll start in like 30 seconds. For those of you who are taking off now, thanks for listening. I enjoyed having you as an audience. All right, I'm starting in 10, 9, 8, 7, 6, 5, 4, 2, 1. Okay, let me show you an issue about how to set the camera angle in a very clever way, especially as you're getting close to the object that you're centering on. Let me turn my camera back on for just a second. So I will stop my sharing there. Okay, so here's an issue that comes up when you're trying to position your camera. Let's suppose instead of this horse, we have this horse's little brother. This is going to be a stand-in for my horse. And let's suppose this is my camera. And suppose I'm coming in from, say, this angle. And what I want to do is, as I'm going by the horse, I want my camera to always be pointing wherever the horse is. So I'm always looking at it. That often happens with satellites that are orbiting planets. You want what do they call it? The satellites are programmed to go by the planet and rotate their angle as they go by it, so they're always taking pictures of it as they go. And that's pretty easy to do. It's not hard. But what is the difference between if you're orbiting at a very large distance? Notice how slowly you have to turn your angle. It's not very fast. But suppose you're orbiting closer to the planet. What's true about how quickly you have to change your camera angle? You notice that you must change your angle much more quickly. And so the view to the viewer looking from behind the camera is much more jarring. It's a much more whiplashy kind of effect. Especially now, what happens? What if you're pointing right at you're going to plunge right into the object, go through it, and then after you go through it, you want to turn around and look at it as you're going backwards. It's always in view whether you're coming at it or going away. The problem is when you get here and you come right into the center, at this moment, you have to turn your camera 180 degrees very fast and then start departing. And when you're doing that, imagine what the viewer sees. Like it's like a whiplash. You're like going, what? What on earth happened to me? It's a kind of a disconcerting effect for the person watching. And so it's not a very smooth effect. It's like it's instantaneous. Let me show you what happened. Let me show you that in action from using the Sierpinski Pyramid that I just showed. And then I'm going to show you a way to solve that problem. So here it is. Here's the problem in action. I'll turn my video off, share my screen again. Let's try that again. All right, so let me go to a small level version of the thing here. And let's rotate a little faster. Let's just watch it go. And what I want you to watch is what happens when we get to the middle of the pyramid and have to turn our camera around so we can keep looking at it as we go. Here we go. Right, so we're almost to the middle. Now we have to turn around. Watch what happens. That was a very quick turnaround. And I'll show you the part of the program that's making that kind of go. This is testing what happens. What if my Z level has reached my middle of my program? This is an accommodation that I'm using to make it smoother. I'm going to turn that smoothness off. Watch it again. Now we reach the middle. You see how that would look kind of instantaneous? That's what we don't want to happen because it's too sudden. The viewer is confused. They think, what on earth happened to my camera? What I want to explain to you is what is the meaning of this? Like there's a long math formula here, which is somehow making this smoother than before. Here's the idea. Half pi is 90 degrees. So what's happening is the angle at which I'm approaching my horse, or the middle of my pyramid, is 90 degrees. So I'm flash on. And I want this to be constant. What this is doing is, as I get close to the thing I want to be towards at the middle of, I want to sort of bend around the thing. Let me stop sharing and I'll show you my camera once again to show you what I'm talking about. Okay, so here's my dot. Here's my location. And imagine my camera's coming in this way. Right now, it's doing this really jarring 180 shift immediately. What I would like it to do is, as it gets close, I want the angle to go away from 90 degrees and circle at a small radius and then turn 180. So it's a much gentler experience for the user viewing from behind the camera. So I come in, as I get close, rather than going straight through and turning, I'm going to do a little loop around it like that, so it's a little bit smoother. Let me show you the mathematics of one way you can accomplish that. So here's a Desmos graph. I have one of my favorite functions of all time is e to the minus x squared. I'm going to use z here because we're talking about the z-axis. And it looks kind of like, actually, let me zoom in. Basically make a little small bump in the middle of my screen. There. And the bump is one thing tall. That's what e to the minus z squared does. You might have seen this before in grade 11 math. Oh, missing our X1. You've seen this function from functions class, right? Thumbs up if you've seen this shape before. Yes, you have. If you make this minus a positive, then it looks like that. If you make it minus z squared, though, something really cool happens. You get a bump in the middle. And this is a very useful function in a lot of physical applications. This is basically what I want my angle to do, except I don't want to be at 0 bumping up to 1. Let's add 90 degrees to this. So that most of the time I'm sitting right at 90 degrees. Pi over 2 is 90 degrees in radians. But as my angle gets close to the point I want to be, I want to zoom in on, my angle is going to go a little bit higher than 90 degrees and then back down to 90 as I get farther away, as I fly away from the object once again. That's the idea. Now I want this, let's look at the size of this bump here. Let's multiply this whole thing by 100. So we're looking at a percentage. Let's zoom way out. and back in. Actually, you know what? Check that. I want the thing to be smaller. Let's really multiply that by like 0.01 or just 0.1. Because often even that bump is too much. So I want to make this a much, like only go up by like 10% of my angle. So 90 degrees plus 10% will be like 99 degrees and back down to 90. That's sort of the idea. Now, in addition to that, we can also make it we can make this not quite so sudden. We can draw this out a little longer by putting this z here in the z squared over something, like over 2. In fact, let's make a parameter of this a. I can make a go from like 1 up to 20. And I can make this happen more gradually, so it's not quite so jarring. So this is very jarring, this is more smooth. So the number I put under here matters. I can also change how much I want to go up or down, so I can multiply this by some number b, where b can be somewhere between 0 and 1. So I can make this flatter. Actually, the b should be in front of, not this. B should be in front of this thing. So I can make that bump larger or smaller, depending on what effect I want to create. Now let's come back to my math program. So here it is. Here's my 90 degrees. I'm going to multiply it by something that's slightly bigger than 1, but only slightly. That's why this number here is very small. Here's my e to the negative something squared, drawn out over a long time. So it's a smooth effect. It's not very large in its bump. Now, why do we have this? What is the meaning of this? This is where I am, and this is the center. So what I'm measuring here is not really z, but the distance from where I want to go. This is where I'm heading, and this is how far away I am from it. All right, folks, that concludes my talk. If you have more questions, I invite you to ask now. Anything you'd like to see or hear about? Emery, you're asking why to use e in the function instead of any other number. So you could use 2. So it doesn't really matter what the base of your exponent is. So if I go back to here, I could replace this e with 2 if I felt like it. That's perfectly okay. But I use e because the mathematics of e is very easy to understand, and the formulas in calculus for dealing with e are very smooth. They're even smoother than working with 2 or 3 or whatever. So that's why I use e. Oh, also, I happen to know, well, I have memorized that e, if I take this b away, take away the a, take away this part here, cool theorem is that when you use e, the maximum of the bump is exactly at 1. Whereas if I use 2, the bump would be somewhere else. Wait, is that true? No, I'm lying. I can make this anything. It's always 1. Oh, never mind, I lied. It's 1 no matter where you are. Anything else? All right, folks, that concludes my presentation. Thank you so much for coming. You've been a great audience, and I hope you learned something cool. And if you liked what you saw today, then definitely sign up for grade 12 computer science next year.